This videotape program was prepared to educate you, the Case Dealer Service Mechanic, on the terminology, components, and operations of hydrostatic systems. Hydrostatic systems were first introduced into the agricultural scene back in 1964, when International Harvester released its Farmall 656 hydrostatic drive tractor. Also that same year, Vibromax introduced its new VTW22 with hydrostatic drive. Over the years, Case has incorporated hydrostatic into several units in the product line and have become leaders in hydrostatic technology. The principles of hydrostatic systems remain the same as those early pioneering models. To get started in understanding more about the hydrostatic systems in today's equipment, let's go over a few commonly used terms. First is hydraulic power. That is simply fluid power, which is transmitted through lines or hoses to a cylinder that converts it into a mechanical output capable of doing work on a load. You see examples of this all the time, like the lift cylinders on a loader, or the hitch lift cylinders on a tractor. Hydraulic systems have greater flexibility than mechanical and electrical systems and can produce proportionately more power than other systems of equal size. When we take this power from the hydraulic system and enclose it into a closed loop, we often call that a hydrostatic system. Even though hydrostatic means liquid at rest, we know that our use of hydrostatic means much more than that. Hydrostatic systems are made up of four elements: the engine, the pump, the motor, and the control system. Since we know about the engine, let's limit our discussion to the three remaining parts of the hydrostatic system: the pump, the motor, and the control system. The hydrostatic pump can come in different varieties. The most common we see is the axial piston pump. Looking inside the main pump housing, you'll find the following components: the rotating group, made up of pistons, slippers, and cylinder block, the swash plate, and the valve plate. This pump can have either a fixed output or an output which is variable. We'll discuss the output of a pump later. The motor in the hydrostatic system can also come in a variety of shapes and sizes. The type most commonly used is the axial piston motor. The relationship between the hydrostatic pump and hydrostatic motor is simply to convert the mechanical energy from the engine into fluid energy, then to convert that fluid energy back to mechanical energy. To control a hydrostatic system requires anything from a simple hand lever to a sophisticated pilot-operated servo control system. The control system lets us determine the speed and direction of the output. Let's look at a closed-loop hydrostatic powertrain used in various pieces of agricultural and construction equipment. A closed loop describes the relationship between the pump and the motor. As you can see, the output of the pump is connected to the input of the motor, and the output of the motor is connected to the input of the pump. The purpose of the pump is to convert mechanical energy delivered by the engine into hydraulic energy. But just how does it do that? Let's take a look. As you've seen, the axial piston pump contains a rotating group and a swash plate. The rotating group is made up of pistons, slippers, and a cylinder block. The swash plate is used to stroke the pistons in and out of the cylinder block, depending on its angle during rotation. By the way, the term stroke is a common term used by technicians when talking about the hydrostatic pump turning on or off. You can say the pump goes into stroke, or the pump comes out of stroke. When the pump is rotated, the slippers connected to one end of each piston slide along the swash plate surface. As the surface of the swash plate is tilted, the pistons in the cylinder block move out and fill on the inlet side of the pump. As the pump continues to rotate, the piston is forced back into the cylinder block and displaces the oil out to the motor. Displacement then describes the amount or volume of oil which is pumped by one stroke of the piston. By varying the angle of the swash plate, you are actually varying the displacement of the pump. Thus, this pump would be called a variable displacement axial piston pump. A lot of words for such a simple device. However, if the angle of the swash plate was designed not to move, the pump would then be considered a fixed displacement pump. Now, let's return to our closed-loop hydrostatic system. Once the oil leaves the axial piston pump, it encounters the input of the axial piston motor. The axial motor is nearly identical to the axial pump and is made up of identical components. Here is the rotating group with the pistons, slippers, and cylinder block, and the swash plate, which is usually at a fixed angle. Let's look at what causes the motor to rotate. To demonstrate this, we have mounted the swash plate on an inclined plane and the rotating group on a vertical axis. The rod represents oil being forced into the motor from the pump. Watch what happens as this force is applied to the pistons. The ends of the pistons get pushed out of the cylinder block. This causes the slippers to push against the swash plate. Thus, the slippers slide down the swash plate, which rotates the motor. The more oil supplied, the faster the motor turns. But another factor also can cause the motor to run faster. If the swash plate angle in the motor can be changed, we call that a variable displacement motor. Let's see what happens when the swash plate angle of the motor is changed. The volume of oil from the pump remains constant. So, as the swash plate in the motor is tilted towards center, the rotating group must rotate faster in order to displace the volume of oil passing through it. As the speed increases, the output force, or torque, decreases. When the motor's swash plate is again returned to a greater angle, the speed will decrease. However, the total amount of torque produced by the motor is increased automatically. The higher volume of oil used by the motor develops more load handling capability. Let's take a look at our example again, using a variable displacement motor attached to a pinwheel. Remember, the volume of oil from the pump remains constant. So, as the swash plate in the motor is tilted towards center, the amount of displacement is reduced with each revolution of the rotating group. Thus, the motor has to turn faster in order to displace the same amount of oil. Now that you have seen how the pump is used to convert mechanical energy from the engine into fluid energy, and how the motor converts that fluid energy back into mechanical energy, we can discuss another factor associated with a closed-loop hydrostatic system: self-compensating lubrication. To hydraulically balance the pistons and to prevent the slippers from wearing out too rapidly as they rotate against the swash plate, a small hole is drilled through the piston and slipper to allow oil to pass through. This oil balances the piston force against the swash plate and prevents high friction between the slippers and swash plate. As the closed-loop oil pressure increases against the piston, so does the amount of lubricating or balance pressure at the slipper. There is also another metal-to-metal contact area in the hydrostatic pump and motor as well. The rear of the rotating block spins against a valve plate mounted to the housing. A slight amount of the closed-loop oil escapes between these surfaces and in turn provides an oil film for the parts to ride on. Thus, the pump and motor have a built-in lubricating system that is self-compensating. Because of normal internal leakage, the closed-loop hydrostatic system will lose a certain amount of oil. The process of replenishing that oil is the job of the charge system. A charge system consists of some very simple components. The components include a fixed displacement pump, usually of the gerotor type, 2 check valves, and a relief valve. The output of the gerotor pump is based upon engine RPM. The pressure is regulated by the charge system relief valve. Charge pressure is now standing by at the check valves. Let's see how the charge system works. To start with, our example pump is in the neutral position. Thus, the only pressure in the system is that of the charge pump. The excess flow produced by the charge pump passes the charge system relief valve and continues on to the reservoir. Very little oil flows past the pistons and through the slipper passage. As the swash plate in the pump begins to increase its angle, one side of the closed loop will increase in pressure. This side will be the output side of the pump going to the input side of the motor. The increase in drive pressure causes more oil to leak past the pistons and through the slipper passage. So, the charge system check valve allows more of the charge pressure oil to enter the closed loop. Many hydrostatic systems are designed to operate in a forward or reverse direction. In order to reverse the direction, all the pump has to do is reverse the direction of flow to the motors. It does that by simply changing the angle of the swash plate across center, thus changing the direction of output flow. However, the charge system must also be able to compensate for this change. To do this, the system uses the other check valve mounted on the opposite side of the hydrostatic loop. Now, when the pump reverses its direction of flow, the high pressure side or outlet side of the pump seats the check ball on that side of the loop. The low pressure side check ball is allowed to open, and once again, charge pressure oil can enter the loop. There is another component which needs to be explained in the hydrostatic loop: the high pressure relief valve. The high pressure relief valve is typically part of the charge system check valve in the pump. When the pressure reaches the maximum allowed by the relief, it pops open, allowing oil to pass by. If the hydrostatic motor encounters such a high resistance that it can no longer turn, the oil being supplied by the hydrostatic pump must be allowed to flow. That's the job of the high pressure relief. There is one in each side of the closed loop, and they allow the high pressure oil to pass by when the motor is unable to displace oil. The oil is allowed to bypass the motor and re-enter at the same point where the charge pressure enters, which is the return side of the pump. At this point, we have covered the main components in the hydrostatic system, the pump and motor. We have seen how they work together in a closed-loop circuit, and how the supply of oil needed in order for both operation and lubrication is provided by the charge system. But in order to completely understand how the system reacts to the operator's demands, we need to examine the control system. With the advent of the variable displacement piston pump, there was the need to control the amount of angle or tilt of the swash plate. Very early methods usually included a simple operator control connected through a linkage to the swash plate itself. The more the operator moved the control, the more angle he would create on the swash plate. In order to achieve more precise control and easier lever movement, The use of servo pistons to operate the swash plate angle was developed. The function of the servo pistons are to simply push the swash plate in and out of stroke. Now, with very little effort, an operator can use a pilot-operated control to move his machine. Here's what is meant by pilot operation. Anytime you use a hydraulic system to gain control of or operate another hydraulic system, that is referred to as a pilot system. Usually, the oil provided by the charge pump is regulated and used as the oil source by the pilot control system. A hand or foot actuated pilot control valve then directs the oil to the servo piston, which controls the swash plate angle. With a change in position of the hand lever, the operator moves the control spool so that pilot pressure oil is applied to one end of the servo piston, thus stroking the pump and causing the unit to move. The operator has an infinitely variable amount of control over the hydrostatic system which he is operating. So not only does the operator get smooth transitions between directions, he also gets the advantages of a torque proportioning system which compensates for an increase in load demand. However, in order to maintain maximum horsepower availability and maximum control, the engine should always be run at full throttle. You have now seen the three major operating components of a simple hydrostatic system. You should remember that the hydrostatic systems built into case agricultural and construction equipment allow the operator a constantly variable method to control speed and a responsive method to change direction. With a basic understanding of variable displacement pumps and motors, the charge system and the control system, you can better troubleshoot and maintain your customer's equipment.